fine. Good morning to everyone. This is Chakudipti of Branch Aeronautical Engineering bearing roll number 2395182114 of semester 6. Today I am here to give a presentation on behalf of AIT Concept Video. The subject is Machine Learning Techniques and Practices. The topic which I have chosen is Role of Prior Probability in Decision Making and Handling Machine or Sparse Data. Introduction to Prior Probability. Prior probability reflects our initial belief about a hypothesis before observing new data. It plays a crucial role in Bayesian decision-making frameworks. Understanding prior probability helps improve decision accuracy, especially with limited information. In many real-world problems, decision-making often involves uncertainty due to incomplete information, noisy data, or limited observations. In such scenarios, prior probability plays a crucial role in guiding decisions by incorporating existing knowledge or assumptions about the systems before observing new data. The concept of prior probability originates from probability theory and is widely used in statistical inference, machine learning, and artificial intelligence, particularly within the Bayesian framework. Prior probability represents the initial belief about the likelihood of an event or hypothesis before considering current evidence. It is often derived from historical data, expert knowledge, or reasonable assumptions about the problem domain. When new data becomes available, prior probability is updated using observed evidence to form a posterior probability. This updating process allows decision makers to refine their beliefs and make more informed decisions over time. In decision making, prior probability provides a foundation when data is limited or uncertain. For example, in medical diagnosis, prior acknowledgement about disease privilege can help in estimating the likelihood of a condition before test results are available. Similarly, in engineering systems, prior probabilities can be used to predict systems behavior based on past performance. The initial information helps in narrowing down possible outcomes and reduce the complexity of decision making. One of the key advantages of using prior probability is its ability to incorporate domain knowledge into occurs due to sensor failures, data corruption, or incomplete observation. While sparse data refers to situations where only a small amount of data is available for analysis. Traditional methods that rely heavily on large datasets may perform poorly under these conditions. Prior probability Traditional methods that rely heavily on large datasets may perform poorly under these conditions. Prior probability provides an effective way to address this issue by filling in the gaps using prior knowledge. Basics of Bayesian interface. Bayesian interface combines prior probability with observed data to update beliefs. It uses Bayesian theorem to calculate posterior probabilities. This approach is fundamental in dealing with uncertainty and sparse data. Significance of prior probability in decision making. Prior probability influences the initial assessments of risk and options. It helps guide decisions when data is incomplete or ambitious. Next, incorporating prior knowledge can lead to more robust and informed outcomes. Handling missing data with priors. Prior compensate for missing data by providing a baseline belief. They allow models to make informed predictions despite gaps in information. Properly chosen priors can prevent bias introduced by incomplete datasets. Managing sparse data scenarios. Sparse data situations benefit from prior by avoiding overfitting. Priors act as regulars, imposing structures on limited datasets. This approach can enhance model stability and interpretability. Handling missing or sparse data is a common challenge in many applications. Missing data can occur due to sensor failures, data corruption, or incomplete observations, while sparse data refers to situations where only a small amount of data is available for analysis. Traditional methods that rely heavily on large datasets may perform poorly under these conditions. Prior probability provides an effective way to address this issue by filling in the gaps using prior knowledge. In the presence of missing data, Prior probabilities can be used to estimate unknown values or to make probabilistic predictions. For instance, if certain features of a dataset are missing, prior distributions can be used to infer their likely values based on known patterns. This approach helps in maintaining the continuity of analysis and prevents the loss of valuable information. Techniques such as Bayesian imputations and expectation maximization algorithms often rely on prior probability to handle missing data effectively. Sparse data represents a similar challenge where the available data is insufficient to make reliable inferences. In such cases, prior probability acts as a regularizing factor, preventing overfitting and improving generalization. By incorporating prior knowledge, models can make reasonable predictions even with limited data. This is particularly useful in machine learning applications such as natural language processing, recommendation systems, and anomaly detection. Types of priors in practices. Informative priors incorporates domain expertise to shape initial benefits. Non-informative or weak priors aim to be neutrally letting data dominate. Empirical priors are derived from historical or related data to inform current analysis. Example: medical diagnosis. Prior based on disease privilege inform initial diagnosis probability. They help in making time decisions even with incomplete test results. Bayesian models update diagnosis as new test or symptom emerge. Next example: machine learning with sparse data. Prior guides learning algorithms when training data is limited. They help prevent overfitting by constraining the model. Proper prior improves prediction in real world data scarce applications. Another important aspect of prior probability is its role in probabilistic modeling. Bayesian models explicitly incorporate prior distributions to represent uncertainty about model parameters. These models combine prior information with observed data to produce posterior distributions, which produce a complete description of uncertainty. This approach allows for more flexibility and interpretability models compared to traditional methods that rely solely on point estimations. The selection of prior probability is a critical step in the modeling process. Priors can be informative or non-informative depending on the level of prior knowledge available. Informative priors incorporate specific knowledge about the systems, while non-informative priors are used when little or no prior information is available. The choice of prior can significantly influence the results, especially when data is scarce. Therefore, careful consideration must be given to ensure that the prior reflects realistic assumptions. In practical applications, prior probability is often combined with likelihood functions to perform Bayesian inference. The likelihood represents the probability of observing the data given a particular hypothesis, while the prior represents the initial belief about the hypothesis. The combination of these two components results in the posterior probability, which is used for decision making. This framework provides a systematic way to update beliefs and make decisions based on both prior knowledge and observed data. The use of prior probability also enhances the interpretability of models. Challenges in setting priors. Choosing appropriate priors requires domain knowledge and careful considerations. Misleading priors can bias results, leading to incorrect decisions. Sensitivity analysis is essential to assess the impact of priors on outcomes. Balancing priors and data. As more data becomes available, the influence of prior diminishes. The goal is to strike a balance where priors inform but do not dominate. Adaptive approaches can update priors dynamically as new information arrives. Future direction and applications. Advances in hierarchical and adaptive Bayesian models enhance prior use. Applications span healthcare, finance, and artificial intelligence. Continued research improves handling of missing and sparse data scenarios. Conclusion. At last, I would like to terminate this project by saying that prior probability plays a vital role in decision making and handling missing or sparse data by providing a structured way to incorporate existing knowledge into the analysis. It enhances the robustness, accuracy, and interpretability of models, especially in situations into the analysis. It enhances the robustness accuracy where the data is limited or uncertain. By combining prior information with observed data, decision makers can make more informed and reliable choices. As technology continues to advance, the integration of prior probability into the decision making process will remain a key component in addressing complex real world problems. It effectively addresses challenges posed by missing or sparse data. Integrating well chosen priors can significantly improve outcome across various fields. Thank you. Thank you for giving this opportunity.